Elon Musk, the visionary behind SpaceX, once boldly predicted a crewed Mars landing by 2026. This timeline, while incredibly ambitious, is now widely considered unrealistic. Developing the necessary technology for a Mars mission is a monumental task. SpaceX's Starship program, while progressing, still faces significant hurdles. Ensuring crew safety on such a long and perilous journey remains paramount. A more realistic timeframe for a human mission to Mars likely extends well beyond the initial 2026 projection. Traveling to Mars presents exponentially greater challenges compared to the Apollo moon landings. The distance alone is staggering. At its closest, Mars is about 34 million miles from Earth, compared to the moon's relatively short distance of 238,900 miles. This vast difference in distance translates to a much longer journey, measured in months rather than days. The extended travel time for a Mars mission introduces a host of logistical complexities. Life support systems must function flawlessly for a far greater duration. Supplying food, water, and other necessities for the crew becomes a significant undertaking. The distance between Earth and Mars is not constant. Due to their elliptical orbits, the distance can vary significantly, reaching up to 401 million miles. This dynamic distance influences travel time, which is estimated to be between 6 to 8 months with current technology. Such a long journey poses significant challenges for the crew. Exposure to cosmic radiation becomes a major concern. Maintaining the physical and psychological well-being of astronauts confined in a spacecraft for such an extended period is critical. NASA's Artemis program, with its focus on returning humans to the moon, serves as a critical stepping stone for future Mars missions. Artemis aims to develop and test technologies essential for deep space travel. This includes powerful new launch systems like the Space Launch System, or SLS. It also encompasses the development of the Orion spacecraft, designed for deep space missions. Furthermore, Artemis will establish infrastructure on the lunar surface, providing valuable experience for building a sustainable presence on other celestial bodies. The Artemis program comprises a series of missions, each building upon the previous one. Artemis 1, already completed, was an uncrewed test flight of the Orion spacecraft around the moon. Artemis 2, scheduled for 2024, will carry a human crew on a similar lunar flyby. Artemis 3, the most ambitious mission yet, aims to land astronauts on the moon, including the first woman and the first person of color. Subsequent Artemis missions will focus on establishing a sustained presence on the moon, including the construction of the Lunar Gateway, a space station in lunar orbit. Building a Martian foothold requires overcoming numerous technological hurdles. In situ resource utilization, or ISRU, is crucial for this. This involves extracting resources like water, ice, and oxygen from the Martian environment. The MOXIE experiment, part of NASA's Perseverance rover, has already demonstrated the feasibility of producing oxygen from the Martian atmosphere. Another key technology is 3D printing, which could be used to construct habitats and other structures using Martian regolith, the loose material on the planet's surface. A Mars base camp, a blueprint for human presence. Lockheed Martin, a leading aerospace company, has developed a conceptual design for a Mars base camp. This ambitious concept envisions a semi-permanent habitat on the Martian surface. It would serve as a hub for scientific research, exploration, and resource utilization. The Mars base camp concept highlights the long-term vision of establishing a sustained human presence on the red planet. It underscores the need for collaboration between government agencies and private companies to achieve this ambitious goal. The challenge of returning home, the Mars Ascent Vehicle. A critical aspect of any crewed Mars mission is ensuring the safe return of the astronauts to Earth. This necessitates the development of a Mars Ascent Vehicle, or MAV. The MAV would be responsible for launching the crew from the Martian surface into orbit, where they would rendezvous with a spacecraft for the journey back to Earth. Designing and testing a reliable MAV presents a significant engineering challenge. It must operate in the thin Martian atmosphere and withstand the harsh conditions of the planet's surface. Charting the course, mission trajectories, and international collaboration. Planning a mission to Mars involves carefully selecting the optimal trajectory. Two main options exist: conjunction class and opposition class trajectories. Conjunction class trajectories require less fuel but result in longer travel times. Opposition class trajectories, while faster, consume more fuel. The choice of trajectory impacts mission duration and resource requirements. International collaboration is essential for the success of any crewed Mars mission. Pooling resources, expertise, and sharing the costs make such an ambitious endeavor more feasible.